Welcome to AP Chemistry at Honega High School. I'm Brian Brown, and today we'll be looking at the fourth section of Chapter 4, dealing with oxidation-reduction reactions, which we often call redox reaction. Now, an oxidation occurs when an atom or an ion loses an electron. That's the definition of oxidation. A reduction occurs when an atom or an ion gains an electron. And we call this oxidation reaction because these two processes occur together. One can't occur without the other. One has to be losing an electron, which the other is taking. Now, the substance that is oxidized is the substance that loses the electron. So the substance on our left here, so this would be our substance that's oxidized. And the substance on our right is the substance that is gaining electrons, so that is what's reduced. Now, a way to remember this, Leo goes grr. So Leo the lion goes grr. Loss of electrons oxidation, gain of electrons reduction. Another way to remember it is oil rig. So these are just memory aids to help you remember what's going on with oxidation reduction for the test. Oil oxidation is loss of electrons. Rig, reduction is gain of electrons. So those are two mnemonic devices to help you remember what's happening with oxidation reduction. Now, why do we call reduction when you're gaining an electron? Gaining is usually going up. That's a gain. So where does the idea of reduction come in with reduction? Well, think about what's happening to your charge. When you gain an electron and are reduced, your charge is going down. So in reduction, what's happening is the charge is being reduced, and that's where we get the name from. One common confusion with oxidation and reduction is they think, okay, reduction, that's when you lose electrons. That's why it's called reduction. No, it's when you gain electrons, and that's because when you gain electrons, your charge is being reduced. Now, in this particular reaction, the neutral calcium has lost 2 electrons to 2H plus when it becomes Ca2 plus. We had neutral calcium. It's becoming Ca2 plus. Oops, there's a little typo there. That shouldn't be there. That plus should be right there. So what's happening is Ca is becoming Ca2 plus. Well, the only way your charge goes up is if you're losing negative things. So we say that calcium has been oxidized to become Ca2 plus. So Ca was oxidized. Now in this reaction, the neutral O2 has gained electrons from the calcium to become O2 minus in CaO. Because remember, it's written as calcium oxide CaO, but it's really Ca2 plus and O2 minus. That's what's inside the ionic compound. So we started neutral and it became O2 minus. So in this particular case, we say that O2 has been reduced because it started out as a neutral charge. O2 is neutral. It has no charge written in the upper right-hand corner, and it's become O2 minus. Well, the only way to become more negative is to gain electrons. And Leo goes grr. Loss electrons oxidation, gain electrons reduction, or oil rig. Rig, reduction is gain in electrons. So we say O2 has been reduced. So when you take a look at these two reactions, you can pick out what's being oxidized and what's being reduced. Now, to determine if an oxidation-reduction reaction has occurred, we assign oxidation numbers to each element in a neutral compound or each charged entity. So we basically go through and we take a look at all of the elements on the left side and on the right side, and we take a look at what has happened to them. Now, oxidation number is an assigned charge. We're taking a look at if it were a charged particle, exactly what would its charge be? So we're going to use this to help see if we've been oxidized or reduced. So one of the things you need to be able to do is figure out what the oxidation numbers are of the elements on each side of the reaction to see if their oxidation number is going up or down. And therefore you know what's being oxidized and what's being reduced. So you need to be able to determine your oxidation numbers. Now, there's a few simple rules we're going to use. And this in the end ends up being very, very, very simple. Elements in their elemental form have an oxidation number of 0. They're neutral. And oxidation number is assigned charge. Well, if you have no charge because you are an elemental substance, then you have an oxidation number of 0. So you're neutral, it's going to be 0. No problem there. The oxidation number of a monatomic ion is the same as its charge. Well, if we have Mg2 plus, Remember, oxidation number is assigned charge. Well, if it's Mg2 plus, it is a charged ion, and it's a 2 positive charged ion. So its oxidation number is the exact same as its charge. So in your neutral, it's 0. So elements in their elemental form, they're neutral, they're going to be 0. And if you are an ion with a charge, that's going to be the oxidation number of that particular species. Now, nonmetals tend to have negative oxidation numbers, although some of them can be positive in certain compounds and certain ions. It just depends on what it's with. But as a general, if you see a nonmetal, it's more than likely going to have a negative oxidation number. So oxygen has an oxidation number of -2. Now, there are exceptions because it can have an oxidation number when it's in a peroxide of -1. And there are also these things called superoxides where it's a -1/2. So remember, oxidation numbers in the end don't have to be whole numbers. But we don't really see superoxides ever. And peroxide you might see every once in a while because it is a common substance at home in your medicine cabinet. Take out that brown bottle. It's hydrogen peroxide. The oxygen in hydrogen peroxide has an oxidation number of -1. Unlike oxygen in most every other substance out there where it's going to be a -2. So you need to remember oxygen is a -2. Remember, if you look at where it's at on its periodic table, it's 2 away from the noble gases. That's good. Tends to form as an ion anyway. And that's what we're looking at is your assigned charge. That's what oxygen typically does is gains 2 electrons. So oxygen typically is a -2. Now hydrogen is a -1 when it's bonded to a metal. So when it's bonded to a metal, one thing has to gain and one has to lose electrons in order to get a stable compound. Well, metals never gain electrons. They only lose electrons. That's their only option of becoming stable. So in that case, hydrogen's forced to be a -1. But when it's bonded to a nonmetal, hydrogen's always going to be a +1. So oxygen is a -2 in almost every instance, and hydrogen is a -1 with a metal or a +1. Other situations related to nonmetals, fluorine, always going to be a -1 every last time. And that's because that's all fluorine does is gain electrons. It's the most electronegative element in the entire periodic table. It is more likely than anything else to grab electrons. It's going to do that, and that's all it's going to ever do. And the rest of the halogen, chlorine, fluorine, bromine, iodine, they tend to form. Chloride and bromide and iodide, they tend to behave the same way. So they're often -1 as well. But they don't have to be -1. Depends on what it's with. So the other halogens also typically are -1 unless they are with oxygen. If they're with oxygen, that's what we call an oxyanion. Remember chlorate, ClO3 minus? Well, if oxygen's got to be our -2, then that chlorine's going to have a positive charge. So when it's with an oxygen, the other halogens besides fluorine, they're not going to be -1 anymore. So the halogens are typically -1. F is always -1, but the chlorine, the bromine, iodine, you got to take a closer look at it because it depends on what it's with. And I'll show you how you figure it out. So it's not really anything you have to memorize. You figure it out from what's given. So we've got oxygen as a -2, hydrogen is a -1 or +1 depending on what it's with, and halogens are typically -1. That's pretty much it. The rest of it we all figure out based upon evidence that's given because the sum of the oxidation numbers in a neutral compound, well, the oxidation numbers have to add up to whatever the charge is of the substance. And if it's neutral, the charge is 0. So the sum of the oxidation numbers in a neutral compound is going to be 0. And the sum of the oxidation numbers in an ion is going to be whatever the charge is of the ion. And that's how we get around some of these things change. So we've got oxygen and hydrogen and fluorine. We always know what they're going to be. The rest of them we just figure out based upon the charge of the compound or of the ion using these two ideas. And we'll practice this a little bit. Now, once we have the oxidation numbers, and we will practice assigning oxidation numbers. We're going to come back to that idea. But remember, the purpose of them was to help us figure out what was being oxidized and what was being reduced in tricky situations. Oxidation occurs when your oxidation number is increasing. So when you lose electrons, your oxidation number is always going to go up. And reduction occurs when the oxidation number decreases. Remember I said reduction, charge is reduced. Well, if your charge is being reduced, your oxidation number is reduced. And that's really where the reduced reduction idea comes in. It's really your oxidation number that's reduced, means you have reduction. So once we see what's happening with oxidation number from the left to the right, we can say whether it's oxidized or reduced. If it's going up, it's oxidation. If the oxidation number is going down, then we know it's reduction. So if you take a look at this particular reaction, we've got copper starting out neutral and becoming copper 2+, and silver starting out as the cation Ag plus 1 becoming neutral Ag. Well, if you go through and assign our oxidation number by the rules we just looked at, remember, if you're a neutral atom, your oxidation number is 0. If you're a monatomic ion, your oxidation number is your charge. So we know that copper is going to be a 0, Ag plus is going to be a plus 1, Cu2 plus is going to be a positive 2, and our silver is going to be 0. Notice we're not really worried about what the coefficients are here. We're looking at the species themselves. Copper, Ag plus, Cu2 plus, and Ag. Those would be your oxidation numbers. Now, if you apply what we just looked at above, what's being oxidized and what's being reduced, well, copper is going to Cu2 plus, and when it does that, its oxidation number is going up, 0 to positive 2. That's oxidation. Silver ions are becoming silver metal, so you're going from a plus 1 to a 0. They're going down, they're being reduced. That's reduction. So when you assign oxidation numbers, it's really easy to see what's being oxidized and what's being reduced. It's much easier to track oxidation reduction looking at oxidation number than it is to try and figure out what's happening with electrons. So oxidation numbers help us figure out oxidation and reduction significantly easier. And that's the key to balancing redox reactions. That's what we're really looking at here is a new type of reaction, oxidation reduction reactions. Now, assigning oxidation numbers. Before we get into how to use them, we need to practice what we just looked at. So I want you to find the oxidation numbers for the elements in each of the following substances. Now, first we have SO2. Now, remember, couple of fundamental things here. Some of the oxidation number always equals the charge, and our O is typically minus 2, our H is typically plus 1, and our F is typically minus 1. I mean, those are our basic things we need to use and apply. So when we look at number 1 here, we have SO2. Now, oops, let me go back to that. For SO2, what's really happening? Well, honestly, we've got sulfur and we've got oxygen. And my rule down here says oxygen is typically a negative 2. So I know my oxygen is going to be a negative 2. I'm going to put that up above. So O is negative 2. Now, what's my F going to, or S going to be? Because I don't really know what that is. So that's my job, is to figure out this unknown. Well, we know it's SO2 and it doesn't have a charge. So that means it's neutral. So if I add up all my oxidation numbers, they have to add up to 0. Well, I have two negative 2's. That's a total of negative 4. Well, if it's going to add up to 0, that means my positives have to be a positive 4. That means, since I only have one sulfur, that it has to be an oxidation number of plus 4. So SO2, the sulfur is a plus 4, the O is a negative 2. And that's how you use these ideas at the bottom. Now, pause the tape and try the other two, and I'm going to walk through them very quickly, but pause and try. You're not going to learn it unless you apply this stuff. So I want you to stop the tape and try both of those real quick. And when you start the tape, you can see if you did them right or not. Now, go to the next one here. Have you paused the tape? Have you tried these, and are you coming back to me? If you are, go ahead and listen. If not, stop the tape now. I can't watch you, but I know what people are doing. Okay, I know oxygen's going to be a minus 2, and there's only one of them, so it's going to be a total of 2 negative. So let's keep it simple. Let's top, we're going to write what we know. So we know oxygen is a minus 2. Now we know hydrogen, when it's with nonmetals, is a plus 1. So we know that's going to be a plus 1. What we don't know is what the Br is. Now remember, just like before, these had to add up to their charge. Same thing is going to happen here. If I've got 1H plus, or 1H, it's a plus 1. And then I've got my Br, and then I've got my O, which is a minus 2. That has to add up to 0 because that's a charge on HBr. It's neutral. So positive 1 plus what? Plus negative 2 equals 0? Well, if Br was a positive 1, that would work. So that's got to be my missing oxidation number. So the total adding up to the charge is how we figure out everything else. Now let's look at this one, number 3, MnO42 minus. I know oxygen's a negative 2, so that's going to be a total of negative 8. But now when I add them up, it has to equal negative 1. So what plus negative 8 equals negative 1? Well, 7 does. So since I only have one Mn, it's got to be a positive 7. So that's how you assign oxidation numbers. Now, while there are many kinds of redox reactions, in this chapter we tend to look at just one type of redox reaction. So we're going to mainly look at what are called displacement reactions. Now, a displacement reaction is a reaction where an ion is displaced or replaced by the oxidation of an element. So a metal reacting with an ion to form a salt or an acid is typically what we're going to see here. And this is the general formula of what we're talking about. We have a substance that used to be neutral and is now going to be have and is now going to have a charge. So we've got a movement of electrons here. This is redox. So in this particular reaction, A is going to displace the B and kick it out. Now B's all alone. So this should look familiar. We gave this a specific name last year in chapter 10 in a pre-AP chemistry. We looked at how we have double replacements and we have combustion reactions and we have synthesis and decomposition. This is what we called a single replacement or single displacement. So the whole single part, if you just say displacement, that's what you have is one thing being displaced and that's it. So it's a displacement. When you have two things trading places, it's a double displacement or double replacement reaction. This is what we called single replacement, or this year we're just going to typically refer to it as displacement. It's a type of redox reaction. So we're only going to look at that and only that type of redox reaction for the most part today, and for the most part in this chapter. Now, in displacement reactions, ions oxidize an element. So we have an element and an ion in a compound is oxidizing that element to make it an ion as well. So the ions then are going to be reduced because they're going to start out negatively charged and they're going to become neutral in this process when they get displaced. Well, when your oxidation number is going from negative to neutral, it's increasing. That's oxidation. And when you have the opposite happening, that's reduction. So when we're looking at the ions in this particular case, the ions then are reduced. Now, in this particular, in that reaction specifically, I should say, when you're looking at what's happening here, um, in that particular displacement, we have a piece of magnesium, and it's reacting with hydrochloric acid. And what you're actually getting here is the magnesium becoming magnesium chloride in solution, and the hydrogen, which used to be +1, is becoming H2 gas. So that's fundamentally what is happening here, is the metal is becoming a metal ion and ends up in solution with the chloride ions, and the hydrogen from our acid is becoming hydrogen gas. So what we really have here is H plus becoming neutral hydrogen in this reaction. So in this particular case, the H plus is becoming H2. And that's why the specific ion I'm looking at here, which is H plus, is being reduced is because it's becoming hydrogen gas in the course of this reaction. I'm going to be a little more specific before I moved on there so I didn't confuse anybody. Now, in this reaction, we have silver ions, and they're going to oxidize the copper metal. So silver is oxidizing the copper metal, and the copper metal is going to become a copper ion. The reverse of that reaction doesn't happen spontaneously. If I throw, let me go back a second, copper into silver chloride solution or silver nitrate or solution or any solution with silver ions in it, the copper is going to take the place of the silver ions and you're going to precipitate out silver metal, which is exactly what you're seeing here when this copper wire is put down in this solution. You see this whitish silvery looking substance forming on the copper wire? That is the silver ions becoming silver metal in solution. So in this particular reaction, Ag is going from a +1 to a 0. It's being reduced. So the silver ions are oxidizing the copper metal, and the silver ions themselves are being reduced in that reaction. Now, the reverse reaction, however, doesn't happen. If I take silver metal and put it in a solution of copper nitrate, or copper chloride or whatever, then no reaction is going to occur. So when we look at these displacement reactions, we can't say just because one happens that the other is going to happen. So we have two possible situations here: silver ions and copper metal, copper ions and silver metal. Only one of those two reactions can actually occur spontaneously. So the flow of electrons, what gets oxidized and what gets reduced spontaneously, is only going to happen one particular way. And you can remember this from last year. How do we know if a certain metal can be oxidized by some acid or some salt? How do we know if that's going to happen? What can we use to predict which of these two things might occur and which one wouldn't? Well, if you recall from last year, this is something that you did with single replacement reactions. We use the activity series. So it's a list of elements in order of decreasing ease of oxidation. So as you go down, they're less likely to oxidize. So this is an example of an activity series. And it's really showing the oxidation reaction that would happen if the lithium became a lithium ion. And remember, the higher up you are, the more likely you are to react. Um, the farther down you go, the less likely you are to be oxidized. So gold, highly unlikely that it's going to be oxidized. So a metal in the activity series can only be oxidized by a metal ion below it. So if I put lithium metal in gold ions, yes, that reaction is going to occur because the lithium is reactive enough to kick out the gold ions and take its place, and you're going to end up with gold metal forming. So a metal in the activity series can only be oxidized by a metal ion below it. And that's something you used last year. If we replace copper, or if we place copper in a solution of silver ions, then Cu2 plus ions can be formed because Cu is above Ag in the activity series. Silver is more reactive, or I should say copper is more reactive. It's higher up on the activity series than silver is. So silver is active enough to cause Ag plus to become plain old Ag. So remember, if the metal is above the ion, the reaction occurs. If the ion is above the metal, the reaction won't occur. So if we put zinc in with lithium ions, no reaction is going to happen because the zinc isn't reactive enough to take the place of the lithium ions. So you can use an activity series to predict whether those reactions were going to occur. Copper and silver ions, copper is above silver, so yes, copper can take the can replace the silver ions, but silver ions can't take the place of copper. So remember when the following reaction occurs, but this reaction did not. The reason why is where they're at on the activity series. So you've got to use your activity series to figure it out. So let's apply this situation. Should we use a iron spoon to stir a solution of lead nitrate? In other words, is a reaction going to occur between the Fe metal and the lead ions? Well, take a look at where they're at on the activity series. Just take a second to find where your iron is and find where your lead is. Remember, if the metal is above the ion, the reaction will occur. In this particular case, if you look at where they're at, probably not a good idea to stir that solution because the spoon, the iron is going to react with the lead. If you look at where they're at, here is iron, and where's lead? Lead's down here. So iron is reactive enough to replace lead ions in solution. So that's exactly what's going to happen. So if my question was, would a reaction occur? The answer would be yes, based on the activity series. If I'm asking you, is it a good idea to use an iron spoon to stir lead nitrate? The answer would be no, because you're going to basically get rid of and destroy your iron spoon through chemical reaction. And that's where we're going to leave off today. So balancing oxidation reactions, that's really what we're going to get into tomorrow. So we're going to end our notes right here.